Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 18, and this problem asks us to draw the splitting diagram for the proton labeled B up here in this molecule, the trans 1,3-dichloropropene, given that the coupling constant, the J for the AB protons is 13.1 hertz, and the coupling constant J for the geminal protons, BC, is 7.2. So let's first go over what coupling constants are, what J values are. So J value is your constant, and that's determining the space in between your peaks in your NMR signal. And if we follow some trends, we know that the J constant value is going to be highest for when protons are trans to each other. So J for trans protons across an alkene is going to be greater than the J for cis protons across an alkene, and that's going to be greater than J for the geminal protons across the alkene. So geminal protons means that on one carbon, you have two different types of protons. So here we have HB, and on the same side of your alkene, so geminal means on the same side of your alkene on this carbon, we have one type of proton on one side and another type of proton on the other side. So across the alkene on one side, there's two types of protons. So this is what we call geminal protons. So if, for example, there was a proton here, then these two would be geminal to each other. But in this case, what we're dealing with here is a trans case, and then we just have something on the same side, but these two are not considered geminal. Geminal will be coming off the same carbon, so these two will be geminal to each other, but that's not the case in this example. So the way that we should go about determining the splitting pattern is, well, let's see, following our n+1 rule, how many neighbors we have. So we're interested in HB, so this is our interest to determine the splitting patterns for this. So we see that we have attached to the central carbon, we have a carbon adjacent to it that is attached to one proton. So we have one neighbor, and we do the n+1 rule, so that gives us two peaks in our NMR spectrum. So we would get a doublet. So our NMR signal would be a doublet. And now we know that this doublet, AB, is going to have a distance in between them, that is 13.1 hertz. And now let's look at this series over here. So we know that attached to this carbon is another carbon, and on this neighboring carbon, we have two protons, we have two neighbors, plus one. So now we have three, so we will have a triplet. But there's two different protons, so we will have, this equation is for just one C, proton C, but we have two HC. So we need to multiply this. What we have is we will have two triplets. We have a doublet of triplets. So we have a doublet of triplets because we have two of these HC protons. Each one of these give us a triplet, but we have two of them, so we have a doublet of triplets. So how this would look is something like this. So one of these protons will look like this, and a little downfield or upfield, we have another one for the other protons. So one of these protons correspond to this, one of the protons correspond to other, and a distance in between each of these peaks, the distance between each of these peaks is going to be 7.2 hertz. So how do we draw this in a splitting diagram? Well, let's draw our protons that generate the smaller J constant values. So we'll draw those first. So it's going to be, we have two protons. Each of them will be a triplet. So we have 1, 1, 2, 3. And then we also have another proton that gives us another triplet, 1, 2, 3. So we have a triplet of triplets. And now the space in between each of these, so space in between each of these peaks is going to equal to our 7.2 hertz. And also between these two as well. So it's obviously not drawn to scale, but the distance in between each of these two peaks, any two peaks, is going to be 7.2 hertz. Now, what do these peaks add up to? Well, if I add all of these, we see that that would all give rise to one peak here and one peak here. So this will give us our doublet peak for HA. And now the distance between these two peaks, the doublet peaks of HA, equals 13.1 hertz. So this is for HA. And the bottom one is for HC and HC. So this is how you determine your splitting diagram for this molecule with these coupling constants provided.